Welcome to A/B testing. In this session, we will learn how to compare two versions fairly so we can make a clear decision. Our example comes from the mobile game Cookie Cats. Why A/B testing? Because we want decisions that are fair and based on data, not guesses. We compare two versions, A and B, with one controlled change. In our case, it is the gate location in Cookie Cats. Users are randomly split into two groups, and we track simple metrics like day 1 and day 7 retention. Think of it like a race on the same track, same weather, same rules. If one version wins under equal conditions, we can trust that result. With this mindset set, let's load the data and see how the two groups look. Industry leaders rely on A/B testing every day. Teams at Google, Amazon, Netflix, and eBay run thousands of tests to improve signups, recommendations, and page layouts. The goal is simple: make decisions with data, not opinion. This culture of experimentation turns small ideas into measurable wins, like a page that lifts conversions by 15%. We will use the same mindset today. With our Cookie Cats data, we will test one change, measure retention, and let the numbers guide the decision. Let's move to the lab. Our goal today is simple: compare two versions of Cookie Cats and decide which one keeps players longer. The only thing we change is the gate position. Control at level 30 and variant at level 40. Our primary metric is day 7 retention and day 1 is secondary. The plan is load the data, compute group retention, summarize effect size, and later run a statistical test with confidence intervals. Keep in mind the clean test rules: random assignment, one change at a time, and a fixed test window. On this screen you see the dataset link and the required columns. We've downloaded the CSV and loaded it as a data frame named DF. Here are the first few rows. Each row is one user with a version, total game rounds, and two binary flags: day 1 and day 7 retention. You should be able to spot both gate 30 and gate 40 in the preview. First, DF info shows 90,189 rows and 5 columns with 0 missing values. That's great. No NA handling needed before we compute rates. Next, duplicates. Count is 0, so we truly have one row per user. Group counts are close, about 44.7K for gate 30 and 45.5K for gate 40. Note the slight imbalance. We'll remember that for diagnostics. Binary check. Day 1 and day 7 flags are clean 0-1. Then a quick base rate table. Day 1 is roughly 44.8% versus 44.2%, and day 7 is roughly 19.0% versus 18.2%. Control minus variant. These are raw means, not yet tested. Activity has a long tail. Median 16 rounds. P90 around 134 and P99 near 493. That tail reminds us there are heavy users, but retention is binary, so it won't distort the rate directly. Before any analysis, we lock definitions so we don't move goalposts. Our experimental unit is the user counted once. Primary metric is day 7 retention, secondary is day 1. Counting rule: if the flag is 1, it's a success. Don't add filters after seeing outcomes. Exposure is installed within the test period, and our analysis windows are exactly day 1 and day 7. Before we start coding, let me give you a quick intuition for the p-value. Look at the bell curve on the left. This shows all the differences we might see just by random luck if there is no real effect. The shaded tails are the rare extreme outcomes. Now think about the lottery tickets on the right. If I win the lottery once, you might say, wow, that was lucky. If I keep winning again and again, at some point you stop believing it is just luck. The p-value measures exactly how much you still believe in luck. A large p-value means our result is very plausible under chance. A small p-value means this gap would be very hard to explain by luck alone, so we start to doubt the no difference story. We will not rely on p-values alone, but this is the basic idea we will use when we set alpha at 0.05 and run our test. To know further about p-value, please review the Colab file. Now look at this curve for day 7 retention. The x-axis is the difference in retention gate 40 minus gate 30. The center at 0 is the world where there is no true difference between the two versions. The blue curve shows the kinds of differences we would expect to see just by random chance if that no difference story were true. The dashed vertical line marks our observed difference, about minus 0.0082, so the variant is a bit worse than the control. If we shade both tails beyond the absolute value of this observed difference, those shaded regions represent outcomes that are as extreme or more extreme than what we saw. When we add up the probability mass in those two tails, we get the two-sided p-value. So this picture is the key idea. P-value is the chance, under no true difference, of landing in those extreme tail areas, or even further out than our observed gap. Here, I declare a small config, id column, group column, allowed labels, primary and secondary metrics, alpha, and a practical threshold we'll use later. Then we run light guards, 1 row per user. Group labels, are the metrics binary? Okay. Finally, a base rate snapshot for the primary metric only. Gate 30 at 0.1902 and gate 40 at 0.820. This snapshot just sets the stage. We're not interpreting significance yet. Now we state the rules for the upcoming test. Null hypothesis, H0. Day 7 retention is the same, so the true difference is 0. Alternative hypothesis. There is a difference in either direction. We are using a two-sided test by default. We also set alpha to 0.05, which means if there is truly no difference, we accept a 5% false alarm risk. We define the difference as gate 40 minus gate 30, so a positive number favors the variant. This simply fixes the rules. The actual p-value and visuals will come later. Now let's talk about statistical significance in this A/B test. The curve you see is the distribution of differences we would expect only from random noise when there is no true effect. The shaded tails on both sides mark the rare, extreme outcomes. A z-test takes our observed difference, turns it into a z-score on this curve, and then asks, if there is really no difference, how often would a gap this large appear just by chance? If that probability, the p-value, is below 0.05, we say the result is statistically significant and we reject the null hypothesis. If it is above 0.05, the data are still compatible with the no difference story, so we do not reject it. An easier way to feel what a z-test does is to imagine exam scores. On the right, each bar is a student's score, and the smooth curve is the overall distribution in the class. A z-score tells you how many standard deviations you are above or below the class average. If your z-score is close to 0, you are a typical student. If your z-score is +2 or -2, you are out in the tails, either very high or very low compared to everyone else. In our A/B test, it works the same way. The z-test measures how far our observed difference is from 0 in standard deviation units. A big Z in the tails means a small p-value and stronger evidence that the effect is real, not just random noise. This plot shows the alpha cutoffs at 0.05 on both tails. The dashed vertical line is our observed difference. If it falls deep into the shaded tails, we reject H0. Remember, a small p says unlikely under H0. It does not tell us how big the effect is. Here, we print the finalized testing configuration and a snapshot of day 7 base rates. We will test two-sided at alpha 0.05, report the difference as gate 40 minus gate mod 30, and interpret positive values as better retention for gate mod 40. Before or during a test, we should know the power of our design. two questions. One, how many users per group do we need to detect a target lift at 80% power and alpha 0.05? Two, with our current sample, what is the minimum detectable effect, the smallest lift we can reliably detect? Smaller effects need many more users. Lower baselines also make detection harder. Keep decisions on the primary metric only. On the power curve, pick a target lift line and read where it crosses 80% power. That point is the required per group sample size. On the MDE curve, find your current per group size and read the smallest detectable lift at 80% power. Baseline day 7 for control is 0.19002 with a plus 2% relative lift target and alpha 0.05. The required per group sample is about 168,357 users. Our current per group N is about 44,700, which yields an MDE about 3.9% relative or 0.0074 absolute. If the business needs a lift smaller than 3.9% relative, this test is underpowered at our current size. Now we split the data into the two groups and compute retention before doing any hypothesis test. The goal here is simple. See the basic story with our own eyes in plain percentages. Before we talk about p-values or confidence intervals, results from this cell are, for gate 30, Day 1 retention is about 44.8% and Day 7 retention is about 19.0%. For gate 40, Day 1 retention is about 44.2% and Day 7 retention is about 18.2%. So, descriptively, gate 30 is a little higher on both Day 1 and Day 7. The important message is, right now these are just averages, not proof. They tell us what we see in the sample, but not yet whether the differences could easily come from random variation. In the next step, we turn these rates into effect sizes, absolute difference in percentage points and relative lift, and then we will run a formal test to check if the gaps are statistically meaningful. Now we take those group averages and turn them into effect sizes that are easier to read and compare. The code calculates two things for each metric. Absolute difference, variant minus control in percentage points. Relative lift, the same difference divided by the control rate in percent. Here is what we get. For day 1, absolute difference is minus 0.0059. So the variant is about 0.59 percentage points lower than the control. The relative lift is about minus 1.32%. Meaning gate 40 retains about 1.3% fewer users than gate 30 on day 1. For day 7, absolute difference is minus 0.0082, so the variant is about 0.82 percentage points lower than the control. The relative lift is about minus 4.31%, so gate 40 keeps roughly 4% fewer users by day 7 compared to gate 30. So in plain language, on both day 1 and day 7, gate 30 is doing better and the gap is larger for day 7 than for day 1. Two important comments. First, these numbers tell us how big the difference is in business terms. A change of 0.8 percentage points may or may not matter, depending on how many users you have and how valuable each retained user is. Second, we are still looking at sample estimates. Even a negative 4% relative lift might be explainable by random noise. To answer the "is this likely just chance" question, we need a formal statistical test. So this step is about size, not yet about certainty. In the next step, we combine these effect sizes with a z-test and 95% confidence intervals to decide whether the day 7 gap is both statistically meaningful and practically important. This is our last stop before the statistical test. Up to here, we verified data quality, locked the rules, checked power and MDE, computed group rates, and summarized effect sizes. Now we run the formal statistical test for our A and B groups. This cell takes the day 1 and day 7 retention flags, counts successes and totals for gate 30 and gate 40, and runs a 2-proportion z-test for each metric. For day 1, the output says, control, gate 30, has a retention rate of 0.4482 with a 95% confidence interval from 0.4436 to 0.4528. The variant gate 40 has 0.4423 with a 95% interval from 0.4377 to 0.4469. The difference, defined as variant minus control, is minus 0.0059. The z-value is about 1.784 and the p-value is about 0.0744. Because this p-value is above 0.05, the day 1 gap is not statistically significant at our usual threshold. In plain language, the small day 1 difference can be explained by random chance. For day 7, the output says control gate 30 has 0.1902 with a 95% confidence interval from 0.1866 to 0.1939. The variant gate 40 has 0.1820 with a 95% interval from 0.1785 to 0.1856. The difference, variant minus control, is minus 0.0082. The z-value is about 3.164 and the p-value is about 0.0016. This is below 0.05, so the day 7 difference is statistically significant. It is very unlikely to see a gap this large purely by chance if there were no real effect. Remember our sign convention. A negative difference means gate 40 is worse than gate 30. So statistically, gate 30 keeps more players by day 7. Here is another way to think about significance and confidence intervals using a bowling game. Imagine the bowling lane as the range of possible true effects. The center of the lane is no effect and the pins are the true value we are trying to hit. Each time we run an experiment, we throw one ball. A confidence interval is like the width of the lane where the ball is allowed to land and still be considered a reasonable shot. If the entire interval falls away from 0, it is as if the ball stays in the lane but clearly on one side, and we call that statistically significant. If the interval still touches 0, it is like a ball that wobbles near the middle. We cannot clearly say whether there is a real effect or not. So CIs tell us not only whether the result is significant, but also how wide the uncertainty is around our estimate. Next, we turn the confidence intervals into a picture. This cell draws 2 separate bar charts, one for day 1 and one for day 7. For each chart, the height of the bar is the retention rate, and the thin vertical lines, the error bars, show the 95% confidence interval for that rate. On the day 1 charts, the bars for gate 30 and gate 40 are very close, and the error bars overlap strongly. That matches what we saw from the test. Day 1 differences are small and not statistically significant. On the day 7 chart, the bar for gate 30 is a bit higher than the bar for gate 40, and the error bars are more clearly separated. This visual reinforces the z-test result. Gate 30 has higher day 7 retention, and the gap is large enough that it is unlikely to be due to chance alone. When you present results, these CI charts are a nice way to help non-technical stakeholders see both the point estimate and the uncertainty around it. In this step, we run a permutation test to build intuition. The idea is, if there is no real effect, then which users are labeled gate 30 or gate 40 should not matter. So we repeatedly shuffle the group labels, recompute the difference in retention, and build a distribution of differences that come purely from random shuffling. For each metric, the code prints the observed difference and an approximate permutation p-value. For day 1, the permutation p-value should be close to the z-test p-value of about 0.07. For day 7, it should be close to about 0.002. That agreement tells us the z-test and the simulation are telling the same story. The histograms that appear show the null distribution of differences when labels are shuffled. The smooth mound centered near 0 is what we expect from pure noise. The dashed vertical line marks our observed difference. The further that line sits in the tail of the histogram, the smaller the permutation p-value and the stronger the evidence against the null. This does not replace the z-test in production, but it is a very helpful way to see what by chance really looks like. Now we condense everything into a simple one-line summary for each metric and then make a decision using the primary metric, day 7. For day 1, the line reads, control equals 0.4482, variant equals 0.4423, absolute difference minus 0.0059, relative lift minus 1.32%, p equals 0.0744, not statistically significant. So for day 1, we do not claim a real difference. For day 7, the line reads, control equals 0.1902, variant equals 0.1820, absolute difference minus 0.0082, relative lift minus 4.31%, p equals 0.0016, statistically significant. So day 7 clearly favors gate 30 and the variant performs worse. Next, we apply our practical rule. We had set a minimum practical target of plus 2% relative lift for the variant. Our observed relative lift is negative 4.31%. That fails the practical rule and even goes in the wrong direction. The decision text says, keep gate 30. The effect is statistical but not large enough in practice. In reality, because the effect is both statistically significant and negative, the safe interpretation is that gate 40 is not an improvement and should not be shipped as the new default. Finally, we run a quick diagnostics block to check for common pitfalls. First, the unit check confirms 90,189 rows and the same number of unique user IDs with 0 duplicates. That means we truly have 1 row per user and our unit is consistent. Second, the binary flag check reports that retention 1 and retention 7 only take values 0 and 1, which is exactly what we want for proportion tests. Third, we test for sample ratio mismatch, or SRM, with a 50-50 expected split. The chi-square test compares the observed counts for gate 30 and gate 40 to the ideal. The output shows gate 30 has 44,700 users and gate 40 has 45,489 users, with a chi-square statistic of about 6.902 and a p-value of 0.0086. This p-value is below 0.01, which is a strong SRM signal. That means the group sizes differ more than we would expect from random assignment alone. In practice, this suggests possible issues with assignment logic, traffic routing, logging, or eligibility filters. Fourth, we look at the activity tails again. Median game rounds are 16, P90 is 134, P99 is 493, and P99.9 is about 1074. The long tail is something to be aware of for deeper analyses, but it is less critical for our binary retention test. Finally, the sanity table shows group-level retention and median game rounds side by side for each version. The numbers are consistent with everything we saw earlier, which reassures us that the analysis is internally consistent. The key takeaway is, because SRM is flagged, we should treat the test as potentially invalid from an experimentation standpoint. The correct next step in a real product environment would be to investigate assignment and logging, fix the cause, and then rerun the experiment. Clean randomization is more important than squeezing extra modeling out of a flawed test. Let's wrap up. In this session, we ran a complete A/B test workflow on the Cookie Cat's data. We started with a simple question. Does moving the gate from level 30 to level 40 improve player retention? We defined our unit as the user, locked day 7 retention as the primary metric, and used day 1 only for context. We checked data quality, split the groups, and looked at the raw retention rates. Then we translated those rates into effect sizes, in percentage points, and in relative lift, so we could talk about the size of the change in business terms. After that, we used a 2-proportion z-test and 95% confidence intervals to ask a different question. could this gap be explained just by random chance under the null? For day 1, the answer was maybe. The p-value was above 0.005 and the difference was small. For day 7, the answer was no. The p-value was very small, the confidence intervals were separated, and the variant was actually worse. When we added our practical rule, requiring at least plus 2% relative lift, gate 40 clearly failed. The one-line decision was, keep gate 30. We also looked at planning tools like MDE and Power, and we saw why SRM, the sample ratio mismatch, is a serious warning sign that the experiment setup itself may need to be fixed. If you remember only 3 things, remember this. Define your unit and primary metric up front. Always report effect size together with p-values and confidence intervals. And write a simple rule that connects the statistics back to a clear ship or keep decision.